has been published originally in 2015, and then I actually did an update just last year and published in a IEEE conference in Los Angeles. Hello, welcome to the meeting. This is Ka Chun, and I'm just about to get started. So what happened was I went through our data and found that we weren't actually analyzing all of the student data that we could, and so two publications. But you should be able to find at least the first one archived. But if you look for me or if you email me, I can always send you a copy of one or both papers. And I'll have these references up again at the end. And Ellen, you can probably archive this PowerPoint as well. So we'll have this available for anyone who wants it. But
great, thanks. I'm also recording this as we go, okay?
Okay, terrific. So this research is actually based on an NSF funded grant. It was a collaboration between me here at the Denver Museum of Nation Science and some colleagues at the Metropolitan State University of Denver. And Metro State is an urban campus. It serves lots of non-traditional students, and they were relatively close by, and so we figured they were a good population to test a study on the use of digital planetariums for astronomy education. And what I want to do is just to give you some background which highlights sort of the need that we felt. And you are free to use these arguments when you talk to your board or donors or anyone else who might be skeptical about planetariums in general. But what I want to do first is to talk about a huge amount of research that has been done in astronomy education. And some of the work has involved what we might think to be a relatively simple exercise, which is explaining the shape of the Earth. But studies have shown that when you actually interview students who are relatively young and ask them what they think the shape of the Earth is, and they can either describe it or to draw it, or in some cases they model it with clay. Welcome. This is Ka Chun, and we're sort of a couple minutes into the presentation. So what we find is that the youngest students might see not only a flat Earth, but an Earth that's tabletop-like, so that it has square edges. And as you might also find students who view a flat Earth with round edges. A child might conceive of a spherical Earth, but the portion that a person stands would remain flat. And you get alternate models where different parts of the Earth are flat that people can stand on. And you can even get somewhat crazy alternative models like this, where you actually have a dual Earth. And the authors who have studied this think that this could be attributed to the fact that students might see pictures of the Earth in textbooks. And so they obviously see a round Earth, but they're also still stuck with the idea of a flat Earth. So they have a dual Earth model. And then over time, usually sometime in middle school or in high school, the alternate models drop out and you get a scientifically correct mental model of the Earth where you have a spherical surface and people can live and stand all over that surface, and the pull of gravity pulls everyone towards the center. And then of course, with the startling prevalence of flat earthers, who knows what exactly is going on with adults now. But I'm just going to move forward from this. But so let's go on to another study. This is from Phil Sadler in his PhD thesis. And what he did was he interviewed roughly about 1,600, or he tested about 1,600 high school students. And in one of them was a visuospatial reasoning exercise. And he asked the students, if you were that person standing in this model of the Mars system with the sun off to the right, what would you see if you were looking at the moon Deimos that's in the foreground of the tabletop? And so the obvious answer is A, where you see the left side of the moon illuminated. And as you can see, only 45% of the students got the right answer. And the second most common answer is 37%, which is C, which is the that picture flipped around. So obviously people also have difficulty trying to place themselves into a three-dimensional situation when they're looking at, let's say, a 2D figure. This is not an easy problem for many people, and there have been studies that actually go back to the 60s and 70s that show this. So this isn't something that's just specific to astronomy. And then finally, if you look at the types of figures that are found in, say, textbooks, so this is Jeff Bennett's book, which has gone through multiple iterations and editions. This is one from 10 years ago. You can see the problem of trying to represent three-dimensional phenomena, which is very common in astronomy, but using two-dimensional figures, that could be problematic. And then when we look at seasons, here is the single figure. Actually, Bennett now has two figures, but this is just one of them showing how seasons can be explained, at least from a space-based perspective. And you have little figures on the globe, and then you also have multiple globes encircling the sun. And again, there could be lots of landmines in this figure as far as students who look at this and who are attempting to build a mental model. We've actually done some work where we've interviewed students and asked them about orbits, what they think the shape of orbits are for planets around the sun. And in this 2010 paper, what we find is that students in our study, actually a vast majority of them think the planetary orbits are not only elliptical, but they're highly elliptical. And so if you look at some of these examples, and we actually ask them as they're drawing this, are we looking at this from the top down, or is this an oblique view from the side? And all of them, for the most part, say this is a top-down view. And in the upper right figure, you even see two different diagrams, one that's labeled side view, and then the other one that's labeled bird's eye view. And so it's very easy for people who look at orbital diagrams online or in textbooks to get a wrong interpretation of what orbits are like. And this feeds into, as I'm sure many of you know, there's a big misconception out there that seasons are caused by the distance between the Earth and the sun. And I think that seeing diagrams like this is one part of it, or hearing the fact that the Earth's orbit is not perfectly circular, and they jump to these extreme ellipticities. And so we can basically come up with a number of different reasons why astronomy, at least a lot of the traditional astronomy taught in introductory classes, is difficult. One is that the physical systems that we are talking about cannot be experienced directly. So we are asking students to build a mental model of these phenomena, and because these are three-dimensional phenomena, often time varying and often at many different scales, it can be difficult to create that mental model. And what the educational research has shown over many decades is that an incorrect mental model can be extremely difficult to change. And then finally, there's also an issue with traditional school instruction, which relies on 2D flat materials like pictures and charts and slides, and even just written descriptions. And then of course, one worry when you use a lot of traditional materials, like even models in a classroom, is that you can possibly introduce new misconceptions or reinforce misconceptions while you're trying to address an incorrect model. And one example of this would be if you were using, let's say, a desktop globe for the Earth and a model, physical model for the moon and a light bulb for the sun. But unfortunately, even with those, it's impossible to place them at the correct distances relative to one another. And so by trying to teach, let's say, seasons, you could be reinforcing incorrect ideas about the scale of the solar system. But thankfully, we've seen a lot of evidence over the years that using computer visualizations and simulations can be helpful. And so obviously, this can be applied to planetarium and to full dome systems. And in this slide, I just wanted to highlight some of the difficulties of learning seasons. So right now on the left are all those topics that are based on what I would call an exocentric viewpoint, meaning you have a God's eye view of the Earth and Sun system. And so these are all of the topics or points that you need to understand in order to make sense of the seasons. But what is also important for the seasons is you also need ecocentric understanding as well. The fact that it's not just what you see from outside of the system, but what we experience when we are sitting on, or standing on the Earth and looking up at the sky as the sun changes its position and altitude over the course of the year, and how that relates to increased or decreased heating on the surface of the Earth. And so this brings us to teaching with immersive virtual environments, and just a fancy term for planetariums. But what's nice about this is that this could be inclusive of other immersive environments or technologies. And what's great about using these type of systems is that we can show multiple frames of reference. So we can be on the surface of the Earth as well as off of it. And we can bridge between these frames of reference by flying back and forth. And so you show a connection between these perspectives. And so we're seeing both the egocentric, the on-Earth viewpoints, as well as the exocentric ones, the ones giving you a God's eye view. We can go through a range of size scales, and also very important is the ability to show time variation. All right, so let's go ahead and start talk about the study. What we did was we had college students who were taking an introductory class at Metro State, and these students, this class was a one-semester class that covered all of solar system and in solar system and outside of a solar system planetary and astronomical sciences. So they basically covered everything from planets out to the edge of the universe. And so oftentimes in schools, you'll see that broken up into two different classes, but this was all done within one class. And so there was a limited amount of time that we could use to cover the different materials. And one group of the students were in our control group. And so these students saw no visualizations whatsoever. They just used traditional classroom materials, globes, 2D diagrams, figures from the book, and so forth. The second group saw visualizations from the planetarium software shown projected on a flat screen within the classroom. And finally, a third group was bused to the Gates Planetarium at the Denver Museum of Nature and Science. And they were shown the same sort of visualizations as in group 2, but within the immersive dome, as opposed to in the classroom. And what we developed over the course of the first year was a set of lecture outlines that were specifically set out to help engage students and correct misconceptions that they might have. We actually had 7 different topics that we looked at. Seasons was only one of them. We created visualization modules specific to these lecture outlines. We run UniView in the dome, so we have all these running in UniView. And then we also created a set of weekly quizzes. And what those did was to determine what student knowledge might exist about a topic pre-instruction. And then we also gave them a quiz that contained questions asking about the topics that we were studying that were contemporaneous with instruction. So roughly within the same week that they either saw the classroom instruction or visited the dome for that particular module, they had a quiz question or a set of quiz questions about that topic. And then finally, we also had the post-instruction set of questions, which were given at the end of the semester. So here are the total number of students and classes. As you can see, we had close to 1,000 students participate. We wanted to get as much data as possible from the groups that were actually experiencing some sort of visualizations. And so you can see that we heavily weighted classes in group 3 and in groups 2. And one problem that we ended up finding was that we had fewer numbers than we would have liked for the first group, the truly controlled group, as you'll see in the next slide. But overall, the numbers are pretty robust as far as the groups 2 and 3. And these classes, those 17 classes were spread out from 2006 to 2010. So we had about 5 years worth of classes. Here is basically the results, and this diagram is a little bit complicated, so I'm going to try and see if I can explain it. So group 1 results are here, and what we're seeing is basically a difference in test scores. So for the red dots, or the red points, is the result when we subtract the contemporaneous scores from the pre-instruction scores from the students. And then the blue squares is the gains that we get when we subtract the post-instruction scores minus the pre-instruction scores. And so what we have are 3 different groups, group 1, group 2 here, and then group 3 off to the right. And as I said, we have some kind of squirrely results for group 1, because as you can see, initially the contemporaneous minus the pre-instruction scores had an effect size of about 0.1. But then when we, at the end of the semester, suddenly the results jumped to about 0.5 for a gain. And, but the error bars are actually pretty wide, and that these error bars scale to the total number of students. Actually, they scale to the square root of the total number of students. And so, so even though this square is right about 0.5, there's a 95% probability that this could actually be somewhere else within this range. So unfortunately, the group 1 results, because of the size of these error bars, they're not quite as diagnostic about this group 1 control group as we would like. So what I'll do is just concentrate on groups 2 and 3. So as a reminder, 3 is the dome group. I'm going to try and just write this in. I really shouldn't be doing this because it looks terrible. And then the group 2 is the classroom group. And so what we see is that immediately after instruction, both groups 3 and 2 have gains, although the group 3 gains are slightly higher than the group 2 gains. But what is really nice is that at the end of the semester, the group 3 students, the students who went into the dome, had better retention, meaning their gains dropped less by the end of the semester than did the group 2 students. Although in the end, I mean, these are almost you could argue that the differences are not significant because they fall within the error bars, but there is, you can see that the error bars for group 3 post minus pre over here and group 2 post minus pre, they lie outside of each other's error bars. And so we're confident that there's a significant difference in the post minus pre results. All right, so what does this mean? I think what we see is an argument for benefits from the visualization software. And there are at least 3 that I can identify. One is that, what we are doing within the visualization software in the planetarium, and this is also true to some respect with the classroom group as well, because they saw the same visualizations but projected onto a flat display, is that the students are seeing a true representation of objects in the solar system with correct scales and orientations and positions of the solar system objects. And so we can at least try to alleviate any concerns that we might have that we're introducing potentially new misconceptions or reinforcing existing misconceptions by the presentation. And then second, our presentations actively move between the ground-based and the space-based perspectives. And so we give students these different frames of reference so that because they're jumping back and forth between the earthbound views of the sky with an orbital view of the Earth, and the instructor at the same time is connecting these 2 perspectives in his or her lecture. And so we're hoping, and we think we have been successful in trying to bridge these 2 perspectives using the software. And then finally, obviously, planetarium software it can show time variation really well, and that, of course, was easily done in our presentations. Now, as to what is causing the difference between students who go to the dome versus students who are stuck in the classroom, I think there can be a number of benefits from immersion that that we speculate on. The study doesn't really address, doesn't give us actual answers, but it leads us to speculate why this might be. And so this can lead to potentially future studies that can help hopefully pinpoint this. But one is that there are limitations to the traditional classroom presentation. So if you think about how many pixels are on display in a typical classroom projector, and in our case, we had projectors that only had a 1024 pixels across. And so what that means is that you can either have a high resolution but small field of view representation of your environment, or you can have a low resolution but a wider field of view, meaning the student can see more of what is being depicted in virtually within that scene. But what happens is that in this case, you get a lot more detail, but you lose a lot of the context of, let's say, where the sun is in the sky, which is extremely important when you're trying to explain seasons from a ground-based perspective. And whereas here, you can potentially have both the sun and lots of other things on screen at once, such as the horizon. And so you get a sense of how high up the sun is from the ground, its altitude. But because you have lower resolution, you're also missing a lot of the details, which might help you understand the scene better. And so, and another aspect of this is that when you're in the dome and and let's say you're showing sunrise and the course of the sun is tracked through the day and all the way up to sunset, it's really obvious for the students in the planetarium to see that the sun is at a certain altitude, and to notice the difference in how high the sun gets in summer versus winter solstices. Whereas in the classroom, this knowledge isn't for free because you don't see it all around you. Instead, the instructor has to point out exactly how high the sun is relative to the as grid that's been overlaid. So as a result, the students in the planetarium basically have lower cognitive load as they're building their mental models, because they can immediately see for themselves where the sun is in the sky, where it's rising towards the eastern horizon, where it's setting towards the western horizon, whereas all of that information has to be explained by the lecturer in the classroom situation. And as a result, in the classroom, you're trying to parse those explanations at the same time that you're building your mental models. And so I think that just puts too great of a cognitive burden on students, and that's why it's more difficult for students to make sense of this. So I just want to put up not only the two publications about that where we talked about seasons, but also a few more additional papers involving some other topics that we published on in the last few years. The most recent one was about learning scale in the solar system using a digital planetarium. But another important one was in 2016, where we looked at how we used planetariums to teach moon concepts. And the importance of that is that, again, in our discussion, we seem to find some evidence that the wide fields of view of planetariums and other really immersive spaces actually have an intrinsic benefit to students, irrespective of whether the concepts that we are teaching deal with spatial phenomena or not. So with that, I will end my presentation, and I'll be happy to take questions.
Thank you, Ka Chun. I would encourage everybody to unmute at this point, and a round of applause for Ka Chun. It was excellent.
Thank you.
I'm also going to stop recording at this point.